Hi, everyone. Thank you all for joining today. For today's seminar, we have Professor Masha Kamenetska from BU. She's an assistant professor joint in the departments of chemistry and physics. She's also a member of material science and engineering, as well as the Nanotechnology Innovation Center. Broadly speaking, her research focuses on single molecule spectroscopy and characterization, and her work has been recognized by awards, including the Air Force Young Investigator Award, as well as the NSF Career Award. So it's a pleasure to have you, Masha, here with us today, and we're going to learn more about Masha's work on engineering quantum properties of molecular circuits with chemistry. So before I ask Masha to join me here, just as a reminder, if you have any questions in the room, feel free to raise your hand to ask your question directly. For those who are listening to us online, if you type your question through the Q&A option, I'll read it and can help moderate the questions for you. And yeah, Masha, the floor is yours.
Thanks. So thanks so much, Farnaz, for organizing this visit. I've really enjoyed my day. Thank you all who have met with me. I've learned a lot. As some of you know, I did do my undergraduate degree here at MIT. So it's a little bit surreal to be back here in this kind of different capacity. What's more is, so I was a course 8 major, so that's physics, for those of you who, like me, might have forgotten. And now, as you'll see, a lot of what I do is molecular in nature. So we'll see how well I do here switching fields. But so, you know, as Farnaz said, my work is interdisciplinary, and my lab broadly focuses on developing and then applying single molecule tools to probe matter on the nanoscale on the single molecule level. Today, I'll focus mostly on these molecular metal junctions, where we can create circuits out of single molecules. So before I jump into that, I just want to give you a broad overview of a little bit of what my lab does. As I said, we focus broadly on probing single molecules, and so that spans kind of the nanoscale range or regime where we have small molecules bound to metal electrodes. But we're also working on biophysical systems using a different class of techniques called optical tweezers to probe kinetics and thermodynamics of biological materials. And then here in between, we're working to apply these tools borrowed from biophysics to more material science applications. And I see Hanil there in the back, who's working on this problem in my lab. OK, so that's kind of a broad overview. And again, before I jump into the specifics, I think it's good for us all to get on the same kind of page in terms of, you know, the motivation. So why go through the trouble of isolating a single molecule so that we can watch it in real time? Well, it's because you know, molecules are dynamic. So I think biophysics community was the first to kind of really articulate this very clearly. If you imagine some sort of biological complex, such as this kind of monster over here, you might realize that a lot of the functionality here comes from the interface between different elements of this complex. So there's intramolecular interactions between, you know, different parts of the same molecule. There's intermolecular interactions between different molecules. And so this complex is dynamic, and these interfaces are constantly changing. And it's very hard to synchronize a large number of these complexes such that they're all in phase. And so if you put a large number of them into a test tube and probe it with some kind of spectroscopy, you're going to get a mess, right? A blur, because they're all slightly in a different phase of their motion. And so if you can grab a single molecule and actually watch its dynamics, you can really get an understanding what is the function and how does the structure affect the function and what are the dynamics. I would argue the same set of, you know, arguments apply to these molecular junctions, which are the subject of my talk today, where you're putting together at least two very different components to make some sort of, you know, functional device, if you will. These are not yet devices. They're still in the basic research phase of their development, but they have some sort of functionality. And this was actually proposed by Avram and Ratner in this seminal paper in the 70s. And what they really kind of focused on and proposed in a revolutionary way is that you can actually design molecules to give you electronic functionality, like they can act like, you know, transistors or diodes and so on. But what I think was underappreciated for many years is the fact that the interface here, which by the way is a significant fraction of the overall size of the system, can't be ignored because the interface is on the same length scale as the system itself, and so you can't just neglect it. The dynamics of this interface will influence the properties. And so you really want to be able to isolate this and study it and see how changing structures affect the electronic properties of the entire circuit. What makes these systems really a unique opportunity, I think, is that you can see quantum effects even at room temperature. Why is, and that's really kind of what I will be focusing on today. So why is that? Well, at the nanometer scale, if you think about the mean free path of an electron in a metal, it's a lot longer than a nanometer. So what does that mean? That means that on the scale of this junction, the electron crosses the junction ballistically without scattering off of phonons. And so because there's no scattering on this length scale, the process, this transport of an electron across the junction, is coherent. Oops, there's the arrow. And so even at room temperature, this coherence is preserved, and we can observe quantum phenomena like quantum interference, and then also use chemistry by manipulating synthetically the structure of this molecule to control and engineer quantum phenomena. Okay, so just another kind of background slide. So how do we actually make these measurements? So for the molecular junctions I just mentioned a few minutes ago, we use a kind of a scanning probe technique where we isolate a molecule between a tip and a substrate. And then so let me show you, here's a typical molecule that we can measure, for example. For longer molecules and softer materials, we actually use the optical tweezer, and these two tools are really kind of complementary in that they span different regimes of length and also of energy. So this scanning probe technique is really ideal for small molecules on the nanoscale because it has exquisite length resolution, and it is quite a stiff probe, which is compatible with the covalent linkages in these short molecules. In contrast, if you want to study van der Waals bonded or hydrogen bonded softer materials, you need a softer probe on the piconewton scale. This is also the scale that's ideal for probing biological complexes. And you can sacrifice a little bit of your length resolution because these are extended systems. So these are really two nice complementary approaches, and we use them both in the lab. And what I won't get to tell you today is about our work on biological polymers. So here's a unzipping of a single DNA hairpin, which is kind of cool to see. Here's the unzipping event at 10 piconewtons or so. And the other story that I won't get to show you today is, and I learned this previously, when I have this pointer, I can't actually play the movies. So if I could, what this movie would show is that these are two gold nanoparticles that we're holding in an optical tweezer in solution, and we can move them relative to each other while at the same time measuring the plasmonic response. So that's another project in my lab that I won't get to talk to you about today. Okay, so as I already mentioned, what I will tell you about are these molecular junctions and how we can observe and control quantum phenomena in these systems. So one of the very few kind of background theory slides, I promise. But so I already mentioned that transport here is ballistic. So this is not like in a macroscopic system where the electron gas diffuses. That's kind of the model of conductivity. Here, the electron crosses ballistically, and that means that transport here is described by the Landauer-Bodecker model, where conductance, this G's conductance, current divided by voltage, so the inverse of what you're used to reading about resistance, that's just the convention in this field. Conductance is going to depend on the transmission T of the available quantum channels in your junction. So if there are many quantum channels, then you sum over them, and you sum over this coefficient T, the transmittance of this junction. And so if you have a single conducting channel with a transmission probability of 100%, then you expect a conductance of 1G0, which is the quantum of conductance through this junction. So it turns out that molecules typically have a transmission probability that's lower than 100%. And why is that? Well, if we kind of do the most simple model of what this system is, we have two metal electrodes which have a continuum of energy states filled up to this energy E Fermi. So all my carriers of charge are at the energy called E Fermi. Of course, we apply a slide bias, which is greatly exaggerated in this cartoon, to drive the system out of equilibrium and drive electrons across this junction. But now as this electron comes to this junction, what it sees actually are these discrete molecular orbitals from the molecule. The molecule is like a 0D system, so it has these discrete spectrum. And so these orbitals are typically mismatched in energy from the Fermi energy of gold. And so what you really have here is kind of your classic tunneling problem, which maybe you remember from back, introductory quantum classes, where the electron is going to tunnel across this barrier. And so the tunneling probability is exponentially decays exponentially with the length of the molecule. The longer the barrier, the lower the transmission probability. And the other thing that it depends on is the height of the barrier. And in this case, the height of the barrier is the energy mismatch between the molecular orbitals. So I should mention I'm using chemistry language here. So MO is molecular orbital. These are just eigenstates of the molecular system. And then the LUMO is the lowest unoccupied molecular orbital. And this is HOMO, highest occupied molecular orbital. This is just chemistry jargon. But the mismatch is what dictates the height of the barrier. And so your conductance will decay faster for molecules that have a wider HOMO-LUMO gap, for example. So that's one way to think about this. There's kind of another way to think about transmission in the system, and that's by realizing that these discrete resonances will broaden when the molecule interacts with the metal, right? So the molecular orbitals will hybridize with the metal, and so the lifetime will shorten, and so these resonances will broaden. And it's the broadening and the resulting overlap of this resonant, of this kind of molecular orbital resonance, the orbital overlap at Fermi will dictate transmission. So energy level alignment is important, and broadening is also important for determining transmission. And this spectrum on the right we often get from calculations, for example, density functional theory calculations, and we will often calculate this and then compare to our experimental measurements of conductance. Okay, so how do we do these measurements? I will go through this rather quickly. It's a modified scanning tunneling microscope, except instead of imaging to get an image in 2D, we're going to operate this in the eye of Z kind of mode, where Z is the axis perpendicular to the surface. And so we're just going to smash and then pull out this tip relative to the substrate. And we're going to do that thousands of times. And if we do this in a solution of molecules, occasionally we trap a molecule in this junction, and we measure the current. Okay, we can do this at room temperature, as I said. We also do this at times at 4 Kelvin, and we collect many measurements to get statistically meaningful results. Okay, am I doing okay with the microphone? Yes? Okay, good. So how do you know that what I'm telling you is correct? We'll just look at the data. So here's a single pull-out trace measured on clean gold. And so immediately what you see is you have these discrete jumps in conductance. This is very kind of not classical. Why are there discrete jumps? Because a single gold atom has one nearly perfectly transmitting conductance channel. So as you pull this junction apart, you thin out the number of gold atoms in the cross-section, and you're removing conducting channels, and so your conductance drops in these jumps of integer multiples of G0. This is very nice because at the very end you have this plateau at 1G0, and when it ruptures you open up this gap and you know it's pristine because you just had a signature of a single quantum point contact, a single gold atom at the junction. Okay, I'm just going to zoom in and show this to you on a logarithmic scale so that you can see that after you rupture that final plateau, conductance drops, and then you have this kind of tunneling through the vacuum gap that you might expect. Okay. We do this, as I said, thousands of times to get statistically meaningful results, and we analyze the data by constructing histograms. Okay, There we go. This is a histogram of 1,000 traces measured on clean gold at room temperature. And so, we don't select any of our data. We bin every single trace we measure. We put into this histogram. And so the fact that we have peaks at integer multiples of G0 means that I didn't just select a very pretty looking trace for you on the left. I do, in fact, very often, in fact, in every single trace, measure plateaus at those integer multiples of G0, and this is my tunneling signature. Okay, so now we're ready to introduce molecules. And so we're going to put molecules that have been terminated. I apologize, there's a little bit of a lag here. There we go. That have been functionalized by some sort of linker group that we know binds to gold. Okay. So in this case, it's the nitrogen and the amine linker group. And so what we see now is that following the 1G0 plateau, we very often start to see additional plateaus at lower values of conductance. And if we bin every single trace we measure, this is 10,000 traces, I believe, we start to see peaks at molecule-specific conductance values. To give you a little bit more evidence that these are really single molecule signatures, I will point out that there's a shoulder here, and if you fit the position of this shoulder, its conductance is exactly double the conductance of the main peak. I should say that actually this question of is this single molecule or not has largely been settled over the last 20 years or so. This field is kind of reaching maturity. Okay, so there's one more piece of kind of tool set that I have to show you, which is another way that we analyze this data is by constructing what we call 2D histograms, where we now, instead of just looking at the conductance and binning the conductance axis, we're going to align all our traces along this sharp rupture and kind of add them all on top of each other to create a sort of heat map. So now what we've binned both the conductance as well as the displacement axis. So this tells us, on average, as you pull the junction apart, not only what is the average conductance, but also how long on average does this molecule stay in the junction before the whole junction falls apart. Okay, so these are 2D histograms, and then here on the right you can see, I don't think you can see my pointer, but a 1D histogram turned on its side. Okay, I hope that's clear enough. And so now we can do some interesting stuff. So this technique is very sensitive to the structure of the molecule. So for example, if I measure conductance of molecules of different length, here measuring conductance of alkanes all terminated with the nitrogen, you see that the conductance decays with length. Of course, we make histograms and we look at the average. And indeed, once this appears, you will see that the conductance decays, as we predicted, exponentially with length. I see it on my computer. I think it just needs a moment. So it decays exponentially with length. There you go. There it is. And as expected, so this is tunneling, right? Quantum tunneling, and it went too far. And the other kind of interesting thing is that the decay depends on which molecular family you probe. So oligophenol, which I don't know who the audience is, so I think it's kind of obvious for a chemist, but I think we all kind of have intuition that this little benzene ring, which is kind of the basic building block of graphene, has the localized pi system, which in graphene results in a lot of the properties of graphene. And in this case, this delocalized pi system means that this set of molecules is more conductive than this saturated set of molecules. And so the conductance decays more slowly. And so this is kind of interesting. This is signature of pi transport, whereas this sharper decay is signature of sigma transport. And so you can kind of understand which one is which by looking at these trends. Okay, so this is quantum tunneling, and this is so sensitive to the molecular structure that something that we're working on in my lab, I won't tell you about it in detail today, but using this technique for biosensing. So for example, we've shown that we can distinguish signals from adenine and adenosine, for example, and so we're working to see whether we can apply this to other biosensing applications. It's a sort of new spectroscopy. Okay, so the main subject of my talk is engineering quantum properties in these molecular circuits with chemistry. And I first will tell you a story about how we can create a single molecule switch or a single molecule sensor, depending on your perspective, by manipulating quantum interference in these junctions. So to do this, I actually have to tell you that I held something back, and I didn't tell you another thing that's important in determining transport in these junctions. So I told you about energy level alignment and level broadening that results in this broadening here. But if my claim is correct, that transport here is coherent, then symmetry will be important, because this electron wave incident on the junction can tunnel across both or more than two molecular orbitals as long as they're nearby in energy. And whether or not the transmitted wave will interfere constructively with itself after it crosses these two available channels, or destructively, that depends on the symmetry of these molecular orbitals. So really, if this seems mysterious, it's actually just a property of the fact that this is a quantum phenomenon. And so if we want to look at the transmission probability, we have to square the amplitude. And in this case, the amplitude is actually a sum of two amplitudes. And so if you square them here, you're going to always get an interference term. And the symmetry of these two will determine whether this is positive, in which case it's constructive interference, or whether this term is negative, which means it's destructively interfering. Okay, and this has been shown before. We're definitely not the first to find quantum interference effects in molecular junctions. There's been evidence of pi-pi interference, where all the channels, the HOMO, the LUMO, and other frontier orbitals are pi in character, and so when the electron crosses this junction, there's interference between the different pi channels. There's also evidence between different sigma channels interfering. But what we showed is that actually you don't need there to be only sigma, only pi. In certain cases, sigma and pi type channels can interfere with it themselves, and this gives you a little bit more kind of tunability, and you can kind of synthetically modify this a little bit more easily. So the specific system we're going to be looking at is this pyrazine molecule over here, which again, it's very well known that if you bind linker groups to a benzene in the para position, again, that's kind of chemistry jargon, you bind a linker group at 1 and at 4, and so this molecule binds to gold through 1 and 4 positions, you're going to get constructive interference. Whereas if you put a linker group at 1 and 3, then you get destructive interference because of the symmetry of the HOMO and LUMO pi orbitals. And what we show is that in pyrazine, we can actually flip this and reverse this trend and then further engineer it. So how does this work? So this is the work of my student Hannah Skipper, who actually graduated, I should say PhD here. She graduated a few months ago. So she realized that this trend of constructive and destructive interferences in benzene, again, it results from the fact that the LUMO is symmetric with respect to where the gold electrodes bind, whereas the HOMO is antisymmetric. And there's actually an extra phase change that you have to account for, because one is HOMO, one is LUMO. Just take my word for it for now. And so this one is symmetric, this one is antisymmetric, and then another extra phase change, you actually get constructive interference. Electron waves add in phase. And again, if you look through and see how it all works out on the 1-3 positions, you see that you will get out of phase addition. And so what's interesting, again, this is very well known. By the way, destructive interference looks like a dip in the transmission spectrum. That means conductance is very low, whereas constructive interference looks like this no dip. So that's the heuristic. Okay, so what happens in pyrazine? So in pyrazine, the introduction of these two nitrogen atoms actually rearranges the electronic structure, right? So now our HOMO is actually a sigma orbital. But what's important is that the symmetry of this sigma orbital is reversed compared to what we had in benzene. And so now if you do the same kind of analysis and you compare the symmetry of the LUMO and the HOMO, you find that you actually expect destructive interference when you connect the molecule in the para orientation, and then constructive interference in the meta orientation. And again, if this seems mysterious, really all you need to do is you need to put two Lorentzian line shapes in the HOMO and LUMO position, and then you need to encode this symmetry that we observe here in the gas phase molecules. And if you just do that and then square the added amplitude, you get a sharp dip at Fermi, which predicts no conductance. Okay, so does this work in experiments? I'm going to show you histograms measured from thousands of traces at room temperature. And so I'm going to compare the conductance of pyrazine, which can only bind to the 2 nitrogens in the para position, to these 2 other molecules, which this one can bind in the para and the meta position. So the 1,3 pathway is available because this thiomethyl linker is a known linker. It binds to gold. And this one only has the meta pathway open to it. And so if you measure conductance, indeed you see no signal, no discernible molecular signal for the pyrazine situation, whereas these 2 have a sharp molecular feature. And what's more, the feature is very similar between the 2, suggesting that in both cases, these molecules bind through the 1,3 pathway and conduct through the 1,3 pathway. So again, we know that the nitrogen can bind because this molecule binds. But somehow, when only the para pathway is available, we get no signal. So it's binding, but there's no signal, as if this doesn't conduct. It's off. Okay, this is interesting. We can look at it in a little bit more detail using DFT. All I really want to say here is that the model that I've used, that I've shown you here in green, and I will show it to you again in a minute, is a very simple model. I just add 2 complex line shapes, and I see that I get destructive interference. DFT has a lot more details. It's a full ab initio calculation with all the details of the junction and the electrodes and the electronic structure of gold. And yet, if you focus on this black trace, which is predicting the transmission of the vertical geometry, and you compare it to what I showed you before here in green, you see a very similar result. So that suggests that this very simple model captures all the salient features of the junction, and you get destructive interference when the molecule is fully stretched out in the junction, which is how we're probing it. This also confirms that the LUMO has pi character and the HOMO has sigma character, so it kind of validates our experimental result. But the reason I think this is exciting is because this is just the beginning. Right now you can start to do chemistry and you can synthetically tune this molecule to tune this effect. So for example, if you add a hydroxy substituent now, DFT predicts now this gray transmission trace, which predicts a much better conductance at the Fermi energy. Why is that? Well, that's because actually by just introducing that substituent, you've again reorganized the molecular orbitals. Now you've pushed this sigma orbital further in energy. You've brought back the pi. Now all 3 of these are fairly somewhat degenerate in energy. They all contribute to transmission. And if you now predict transmission based on the addition of 3 components with the symmetry we observe here, you get this green trace, which again matches very well with the DFT calculation, suggesting that now we've kind of, tuned the conductance just by tuning the structure of the molecule. What's even more exciting is now what happens if you deprotonate that hydroxy substituent? Well, now you've totally shifted your spectrum and you predict a sharp turn-on of conductance. You've kind of, made destructive interference go away. So does this work? Well, I probably wouldn't be telling you about it if it didn't. So here's the measurement of this hydroxypyrazine in neutral pH conditions. This broad feature over here is well known to be due to this pi-pi stacking of multiple molecules in the junction. It's not what we're looking for. If you now just add a drop of base literally on your junction, you see a sharp turn-on of conductance. And you can see it here in the 2-dimensional histogram, these very flat plateaus. Why the unexpected thing is that there were 2 peaks. Why there are 2 peaks? Well, here's the paraconductance we think from DFT calculations. And it just so turns out that this molecule can also bind through this deprotonated phenol or the oxygen, which we later on kind of looked into more detail and found that indeed phenols bind to gold. So bottom line is, by engineering these molecules or synthetically tuning them, we've turned off destructive interference. And so now we have this sort of, again, either from, depending on your point of view, either a pH sensor or a switch where conductance is off in this state. And then once you remove the proton, you turn conductance on. So, so hopefully I convinced you that quantum effects are relevant in these systems. And so the next story I will tell you, and maybe I'll pause and see if there are any questions before I move on to the next story. Yeah, in the back. Oscillation. So everything here is DC. It's DC current. So I don't know exactly what oscillation you have in mind. Oh, sorry.
I think they're done with the question.
All right. Okay, so I'll continue, and then if there's questions, just stop me. So the next story I'll tell you is how we can use actually radical character to engineer conductors or single molecule conductors in these systems. And so in the very beginning, I told you that conductance decays exponentially, which makes this a very sensitive, it's a very sensitive system for kind of sensing different molecular structures. But if you're trying to think of how can we use molecules for some sort of real-world application down the line, or just how can we simplify studying these systems, it's actually not trivial, because it means that beyond about a nanometer or so, your conductance is 0, and so a molecule longer than a nanometer, you can't study it because you can't detect it. So it would be great if we could find a way to reverse conductance decay. And so I'll tell you a story that shows that we actually can. And so it's a recent development that's kind of turning, by us and others, but turning this whole field on its head a little bit. So, topological phase transition, kind of a loud buzzword, but bear with me if you will. So this was a suggestion by Hoffman as well as Jelinek, showing that a single polymer, and this will be demystified in a second, can actually have 2 distinct or more topological phases. And if you can switch this phase, you can go from something that's rather boring and has a wide band gap and doesn't conduct very well, to something that has a very narrow band gap and is a good conductor. So what are these topological phases? So it turns out that you can actually think of them, or they're actually synonymous with resonance structures. So a typical, prototypical system like polyacetylene, of course, is really only stable in this form. It's not possible to get it to this structure, but nothing keeps you from drawing that structure. And if you kind of draw the analogy to topological states, you realize that in this case, you generate this electron density at the edges, and these electrons are radicals, right? They're unpaired, and it's constraint. There's just not enough electrons to pair them up if you move your double bonds to these positions. And so this is our topologically trivial closed shell system, and with the same number of electrons, we have this topologically non-trivial phase, this topological insulator, and you can actually see it in STM. So this is, again, is the work by Jelinek, showing that by synthetically tuning this polymer, you go from the kind of typical delocalized HOMO orbital to this HOMO orbital where there's increased density of electrons on the edges, and so that's your topological insulator phase. And so a few years ago, the group of Latha Venkataraman at Columbia showed that these topologically non-trivial phases actually result in this inverse conductance decay. So for example, cumulene, which I'll talk more about why it relates to topological insulators if it's not obvious to you already, but if you measure cumulenes as a function of their length, instead of the typical decay in red, you now see that the conductance of these molecules actually grows as you make the molecule longer. This is a cartoon. The actual data is shown here. It's a little hard to see. I'll zoom in for you later, but there's a slight growth of conductance as the molecules get longer. And a similar situation also happens if you make these charged diradicals. So these are dication diradicals, and if you look at this top line here, which is the relevant experimental line, again, the conductance stays mostly flat as you add extra benzene rings here. So B1 is just one benzene ring, and B3 is 3 benzene rings, and so on, and conductance stays, at least doesn't decay, and then as you make the molecule even longer, you revert to this traditional decay of conductance. And so we were interested in seeing whether we can push this trend further. Can we make molecules that as you make them longer, the conductance keeps going up. And of course, we had to pair up with some synthetic chemists, or magicians as I call them, because they make these wonderful materials. So Mike Haley at University of Oregon and my student Brent kind of realized that these sets of benzoquinone derivatives that they make are good candidates for this study because they have intermediate diradical character. So I have to apologize, there's multiple notations with how you denote diradical character. So in this talk, I'll mostly use this convention delta. And so I don't know if you remember, I had this slide where -1 means fully diradical, and +1 is boring closed shell system. And so the fact that these are close to 0 means they have significant diradical character kind of just in neutral conditions. So where's the diradical character coming from? Again, it's probably, well, it wasn't obvious to me because I'm trained in physics, but it turns out that this benzoquinone structure there's stability conferred by making this benzene aromatic, and so the penalty, energetic penalty paid for splitting up this lone pair is made up for the aromaticity benefit, and so as a result, you get this resonance structure between the two, and both of these resonance structures are present and contribute in solution. Okay, so one more thing is that they've engineered these thioanisole linker groups which have a thiomethyl in the ends, and that allows for this molecule to bind to gold and allows us to trap it in the junction. So what do we see? Okay, so I'm going to show you conductance histograms of a series of these benzoquinone derivatives. So this is BQ1 to BQ3. And if you make a conductance histogram of measurement made at low bias, you immediately see this very drastic inverse conductance decay, or anti-ohmic conductance, as we call it, where the longest molecule has by far the highest conductance by a few orders of magnitude. You can make a two-dimensional histogram just to make sure that you're not just somehow, I don't know, reacting these molecules. And this gives you a nice check because you see that as the molecule gets longer, the plateau, the kind of length that this molecule persists in the junction also gets longer. So that's a nice test that, for example, this one is the longest, that we're measuring what we think we're measuring. If you go to higher bias, this is about 200, 300 millivolts, this effect gets even more exaggerated, where again, the conductance of the longest molecule is a few orders of magnitude higher than that of the shortest molecule. So I can just kind of simply summarize this by plotting the average conductance as a function of molecule length. Suspense. And you're going to see, basically conductance goes up as the molecule gets longer. And again, ta-da, to emphasize now, instead of decay, right, beta is now negative, so we have growth. So this is inverse conductance decay. Okay, the really neat thing about the system is that unlike previously measured diradicals, these are neutral and quite stable. And so we can actually ramp the bias and collect IV curves to characterize the conductance at a variety of bias voltages. So we can collect IV curves on thousands of such measurements. So that's what I'm showing you here. This is now a 2D histogram of IV curves that I've added up on top of each other. And I've plotted the average behavior with this white line. And don't ask me why, but in this field, it's very common to plot IV curves on a semi-log scale, so it's hard to tell whether something's linear or not. So for that purpose, I've plotted these dashed, or rather Brent, my student, plotted these dashed curves, which are actually linear IV curves. And so right away, you see that these IVs are not linear. And that indicates that you have a molecular resonance within range. So as you open the bias gap, you're starting to hit these resonance peaks, and that indicates a small HOMO-LUMO gap in these systems. Okay, so plotting this all on top of each other so you can compare the conductance of these series of molecules, and I've also converted current to conductance by dividing by the voltage. You see clearly, first of all, that the HOMO-LUMO gap, which you can kind of, is this kind of width between the turn-on of current is a proxy for HOMO-LUMO gap, decreases with molecule length. And that's what you expect for really any molecule, like your particle in a box. You make the box bigger, the homolumo gap shrinks. But what's really remarkable in this system is that the zero bias conductance increases. And it increases by 2 orders of magnitude, which is not something that's been observed to date. And so why is this happening? So if you allow me, I know I'm running a little bit long, but I'll try to go through this fast because it's kind of, I think this is exciting. But to understand what's going on, you have to kind of go back to your tight binding model, which is synonymous with 1D SSH, and parameterize the system to understand why we have these closing homolumo gaps and why we have this increasing conductance. So polyacetylene has been worked out years ago, and one way to kind of understand the different topological structures is to realize that the double bond is just really a hopping parameter. Where there's a double bond, the hopping probability is higher. And so if you describe the hopping probability in terms of delta like this, then all you have to know is that when delta is greater than 1, you have this kind of structure where this is higher hopping probability, so you have a double bond there. And when delta is less than 1, then you have this other topological state where now you've moved your double bond over. And so by parameterizing like this, you can now just write your simple tight binding Hamiltonian for those of you who are interested. And now you can solve it as a function of delta because T1 and T2 depend on delta. So when you solve it for different values of delta, you get the following. You get your boring wide bandgap molecule when delta is equal to 1. You get narrowing homolumo gap when delta decreases. And finally, in the topological state, you get no gap. You get a gapless semiconductor, okay? So this is just extrapolated for all values of delta. And now we can take this spectrum. These are just eigenstate solutions to this tight binding Hamiltonian, and we can use non-equilibrium Green's function to calculate transmission. So all you have to do is I'm just going to take these resonances, and now I'm going to predict transmission, okay? So for this boring wide bandgap molecule, you get wide bandgap, and so you have low conductance at the Fermi energy. For the intermediate case, you have a narrower homolumo gap, and so you have higher conductance. And for this topological system, you get no gap. But of course, it's impossible to stabilize the system. And so I'm going to look at this delta equal to 0 case, the intermediate case, because there's actually a physical analog to this, and we can see whether this model agrees with experimental results. So the physical model I'm going to use is cumulene. I know it's not the same exactly, but it's a system where you have perfect delocalization because you have these double bonds at every site. And so I think this is a reasonable approximation to the cumulene case. And the cumulene case has been measured experimentally, and I already mentioned to you that what they measured is a very kind of gradual, slight increase in conductance. So if you look here, it's all within 1 order of magnitude. It's within actually half an order of magnitude. So it's basically flat. You make the molecules longer, and the conductance stays flat. And if you look here, that's exactly what our model predicts. So this 1D SSH predicts that you make the molecules longer, but the conductance here at Fermi, which is where we measure it, stays the same. So how can this be? So the only way that you can have a closing homolumo gap, but a conductance that doesn't increase, is if you have some sort of destructive quantum interference, canceling the fact that the gap is closing. So this is really a signature that there's destructive quantum interference effects at play here that keep your conductance low. And this is just showing that if you look at delta equal to 0, the CQI terms, the constructive interference, really cancel out the destructive interference, and so you just get flat conductance, no enhancement. Okay. What about these molecules? And I will just reveal the result that there is no such destructive quantum interference in these molecules, and that's why you have this dramatic increase in conductance. So just briefly, how do we see this? We have to remake our 1D SSH model for this cyclic system. Again, these are a bunch of details, but we have to introduce 2 more hopping parameters and then make sure that at delta equal to 0, all the hopping parameters are the same so that you really have this fully delocalized system like you expect. So if you do this parameterization, you can solve for the eigenvalue spectrum of the system. Here it is. And now you can predict transport. Okay, you can predict conductance. So I'm going to show you transmission curves for this. Let me just go ahead for this BQ series that you measure. And so if you zoom in at 0, you see that indeed in this case, this model predicts that as you make the molecules longer, the conductance increases. And this is consistent with what we see in experiments, so that's always a good thing when that works out. And if you look at the contribution of constructive and destructive quantum interference, you see that in this case, constructive interference dominates destructive interference effects, again, in contrast to the cumulene case. So, the really exciting thing here, I think, is that these, not just that we have this dramatic increase in conductance anti-ohmic behavior, but that this is just the beginning. So, maybe I'll just skip this term. Basically, these systems are highly tunable. And the model predicts, so this is the BQ1 series that we've measured, plotted on the scale of diradical character. And I apologize, here I'm using the diradical character measurement that's more common in synthetic organic literature. But the point is that using this scaffold, the BQ scaffold, which looks a little bit like flakes of graphene here, and by adding substituents on the side, you can further tune diradical character. And if you can tune diradical character, you can tune the conductance enhancement. And that's indeed what we see. So we've measured the conductance of these kind of derivatives, which have these extra thiophene linkers, which they don't bind to gold. All they do is they stabilize the diradical, and so they increase the diradical character. I realize there's a little, this actually is, again, a thioanisole, so the molecule binds in exactly the same way as the previous set of molecules. But the key here is now the conductance enhancement is further enhanced, right? So this is analogous to BQ1. It has higher conductance than BQ1. This is analogous to BQ2, and it has at least an order of magnitude increase in conductance relative to BQ2. And so, if you can synthetically tune these molecules, you can tune your conductance enhancement. Okay, so that's the end of this kind of section. Again, hopefully I've convinced you that these graphene flake molecules have significant diradical character, and if you can synthetically tune them, then you can manipulate this quantum effect to create your functional, highly conducting molecular junctions or other things that maybe you can imagine. Okay, so I'm out of time, so I won't get to tell you about formation of 1D metal organic molecular wires. I'll just, put this hopefully exciting picture up on the screen, and I'm happy to talk to you about why it might be exciting to try to incorporate metal atoms into the junction, and why that's an interesting thing to pursue. And with that, I just have to thank my group. This somehow doesn't work the way it's supposed to work. I just want to find the picture of my group, and I want to thank them. I really have a fantastic group of students. I'm very grateful to be working with all of them, and I have great collaborators and funding sources, and I want to thank you again for your attention. I'm happy to take any questions.
Masha. For a wonderful talk, so we have time for a few questions.
Hi, thank you. I'm curious, what's the smallest molecule, or in that last part we didn't get to, the fewest number of atoms you can pinch between the gold or get between the gold in terms of like nucleons?
Yeah, so so you always have the linker group, which let's count that as one atom, like a nitrogen in an amine case. So you need that to anchor to gold. And then between that, the smallest reliably you can catch is 2 carbons or 2 nucleons. So that's half a nanometer, roughly.
Thank you for the great talk. So when you were showing your IV curves for the BQN series, it seemed like going from BQ1 to BQ2, there was a very strong enhancement of the conductance value that you saw. But then from 2 to 3, there seemed to be very insignificant enhancement. Do you have any explanation for this?
Yeah, so it's definitely nonlinear. I mean, basically, you can never exceed a conductance of 1G0 here. So, as you make something longer, in the best case, it's just going to asymptotically approach 1, and that's kind of your limit here, because you only have the, it's just the one channel. So, that's basically why. So you get a large enhancement initially, but then it starts to asymptotically approach. But, actually, there's probably more to it. So, at some point, this has to break down, right? There's going to be localization, and your conductance that's going to break your coherent, the coherence in the molecule, and the conductance is going to start decaying. So is that partly what we're already seeing? Perhaps, yeah.
Hi, so in these diradical systems, you have an even number of electrons, but they're kind of separated from each other. Do you open up any cool spin physics with that, or is the fact that they're still like all paired kind of wash that out?
Well, certainly. So, part of why these molecules got attention in the literature, not in our work, but previously, is because actually there's the exchange energies is fairly is fairly small. So certainly people are interested in studying the triplet state, and I think you can access that at like as little as 50 degrees Celsius, or no, 50 degrees above room temperature. So, that was always in the back of our minds. So we don't see anything yet. Based on what we've done, my intuition is that triplet or singlet doesn't actually matter for conductance. I don't have solid evidence for that. So there might be, we just haven't found it yet. And of course, creating different spin multiplicities is one of the motivations for incorporating metal atoms into your junction, right? You can have all sorts of open shell character, and you can have different spin quantum number depending on the metal you incorporate. So we haven't seen anything yet, but yes, that's certainly something we're interested in.
Thank you for this. Hey, so with the Haley molecules, they're required to have, just for stability, they have these big bulky groups, and so the phenols are exactly
yes, perpendicular.
There's no overlap there. And so you have this intervening little, junction between in each side. And so I just wonder how that, earlier you had direct bonding.
Exactly.
And so your gold is separated. How does that figure into all your calculations?
Yeah. So I forget who I was talking to today, and we were saying that, 10 years or so, the thought was that you actually wanted as direct a contact to the molecule from the metal as possible, because that's how you maximized conductance. So that's kind of to your point. But in these molecules, we have decoupled them from the gold. And it turns out that when you have these radicals, this decoupling linker is actually essential to getting to seeing this effect, because if you couple it too strongly to the metal, the diradical will just escape into the metal, and you will not see this enhancement. So actually that perpendicular, as you were pointing out, the pi system is perpendicular, so the diradical is really kind of decoupled from the metal, seems to be key to getting this functionality.
Yeah, I guess I was thinking it almost looks like you have a little quantum well between the two.
I see.
And, you have a barrier.
Yeah.
That's how I would have thought about it, is a quantum.
Yeah.
Two little barriers on either side, but.
The wild thing, and the reason why it took me a while to get my mind around this, is that the conductance of that whole entire huge molecule, for me that's huge, with the thioanisole, the kind of graphene flake core, and other thioanisole, the conductance of that whole thing is higher than the conductance of a single thioanisole. So the linker, so somehow so I don't know if you can describe it by this double barrier model. My instinct right now is no. There's this fundamental kind of different transport mechanism happening here. Yeah, but maybe we can discuss more. Yeah.
So I'm going to ask one of the questions from our online audience. So the question is asking, how can we make functional practical electronic devices with these molecular junctions, and what are some of the applications?
That's a great question. Functional, yeah, I don't know, but maybe you know, Farnaz. Maybe that's a question for you.
Can you comment on some of the applications?
Well, I mean, you know, I guess I would say that, you know, the fundamental limit to Moore's law, why can't we shrink down our electronics even further? I mean, one way to kind of restate that problem is that as you keep shrinking your electronics past the 10 nanometer size scale, you no longer have bulk material, which is what you're relying on to create the functionality. You have some sort of 0D, right, object, either a quantum dot, if you want to think about it that way, or a molecule. These are all 0D materials. And so if we want to push our electronics to smaller sizes, we need to understand the kind of fundamental charge transport processes taking place on this size scale. So that's kind of the motivation. How to make a functional device? Yes, I don't know.
A lot of work in that area.
Yes.
Any other questions?
Thank you. Really fascinating, thank you. I have a related question to the one that was just asked about any immediate application to improving quantum coherence in computing.
Yeah, the tricky thing here, it's kind of misleading. I probably can't answer, well, I definitely can't answer this fully in a short time period. But so the effects we observe are due to coherence. But the molecule crosses this junction in, I don't know, femtosecond time scale. And you know, on a much slower time scale, this is all at room temperature, everything's wiggling. And so in this tiny moment of time when the electron is crossing, it's not scattering, everything's coherent. But the next time another one crosses, the system has fluctuated. So yes, we're studying coherent phenomena, but they're very short-lived. And how we connect this to quantum computing, you know, is not clear to me. But certainly people do make qubits out of molecules, but to do that, they have to cool the system down to the millikelvin temperature. So yeah, we're certainly thinking along those lines, but I'm not sure I have a good answer for you. Right. I'm glad I sold you. But it's true. But how to use it for quantum computing, yeah, it's not obvious. But at least we can probe these. I mean, the nice thing is that we can probe these fundamental phenomena without having to cool to millikelvin temperature. And I think that gives us a lot of benefits. We can repeat the experiments many, many times. We can easily modify things without spending weeks, you know, creating these systems. So, yeah.
So we have ran out of time, so help me thank Masha again. Thanks, Masha. So we are going to have a reception until 4:30, so Masha will be here. You can still have a chance to talk to her. There's also food, so please help yourself.